Hey guys, what's up everyone? Today I'm going to be talking about the ratio test. So with the ratio test, we look at a given series, AN, looks something like this, and we are determining as to whether this series converges or diverges. With this ratio test, we are looking at the limit as n goes to infinity for the absolute value of an plus 1 over an. And we basically, if we have n, we just add 1 to it basically, and this will give us a limit. And the limit tells us as to whether this original series converges or diverges. So if the limit is less than 1, then this tells us that this original series is going to be convergent. And it also tells us that this original series is absolutely convergent. So this will tell us that the original series is convergent and absolutely convergent. Because if something is absolutely convergent, it makes it convergent as well. So this tells us that the series will be convergent, and also the series will be absolutely convergent. And when the original series is absolutely convergent, it just basically means that the absolute value of this is going to be convergent. So this absolute value, right, is going to be convergent. That's what absolutely convergent means. Now, if the limit is greater than 1, however, this will tell us that the original series is divergent. And then lastly, if the limit evaluated for this here is equal to 1, then we can't conclude anything about this original series. So it will be inconclusive. And we don't know if it's convergent or divergent. If it's inconclusive, that means we will have to probably use a different method to determine as to whether this converges or diverges. So we're going to write that for this we will have to use another test or method to determine as to whether this series converges or diverges, and we will not be able to use the ratio test if L equals 1. So say we have a series that looks something like this, and we are trying to determine as to whether it converges or diverges. So we're going to have to find that limit, right, using the ratio test. And then we will have to recognize that we have to add 1 to the ends in order for us to complete the top term. So we are going to do that. Here it's just going to be -9 to the exponent of n plus 1. And here we are going to add 1 to n as well. And then we are dividing by an, which is simply just this term, right? This whole thing is our an, so we just copy it. And then now we have to recognize that this is division, so we can just change it to a multiplication symbol and flip the second fraction. Here n plus 1 plus 1, well, it's just going to be n plus 2. So we're going to write n plus 2. And then we change this to multiplication, flip this. And then once we flip it, we can see that, well, this is -9 to the exponent of n plus 1. And n plus 1, well, we know that we're basically adding exponents, and according to exponent laws, just means that we're multiplying. So, to illustrate, this is what I mean. So we have -9 to the exponent of n times -9 to the exponent of 1, because we just add these two exponents when we multiply these two together. Plus 2 factorial times n plus 1 factorial for -9 to the exponent of n. And we see here this is the same thing as the top and bottom, so we cancel these out. And then what happens next is -9 to the exponent of 1 is just going to be -9. n plus 2 factorial. Well, you know, if we have, let's say, 5 factorial, it's the same as 5 times 4 times 3 times 2 times 1. So it's like the one less than it to be multiplied to it, and then the one less than it. And it can also be written as 5 times 4 factorial here, because this whole thing is 4 factorial. So applying the same concept here to n plus 2 factorial, we can rewrite this as n plus 2 times n plus 1 factorial. And then we can basically cross it off with this one. This move is strategic, so we can eliminate these two. So we're going to eliminate these two, and then what happens next is we are going to find that this is just -9, and then this is n plus 2, it's just 1, so we don't have to write that. And then from here we can see, well, if there's that absolute value sign, we just have to get rid of that negative, and also the bottom's just going to be positive anyways because it's n plus 2, right? So we're adding, like, n can only be from 1 to infinity, and it's positive numbers, so we're just adding more positive numbers to it. So the denominator is going to be positive. So we get rid of the negative sign, and I'm just going to get 9 over n plus 2. And then if you put in infinity to n right here, it's just like you're making this denominator really, really big. When you get a really big denominator, compare to the tiny, tiny little 9. Tiny 9, big denominator makes this number very, very small. It shrinks the number. And so this would mean that this number goes towards 0. And therefore this is 0, and this is our limit. So our limit in this case is equal to 0. And we know 0 is less than 1. Our limit then is less than 1. And if our limit is less than 1, by the ratio test, this tells us that this given series, is absolutely convergent. So the given series, which was that looks like this, is absolutely convergent. So that means this series with the absolute value converges. And by definition, if something is absolutely convergent, that means the original series itself is also convergent. So therefore we can conclude that our original series, this original series, converges. Because it is absolutely convergent. So it converges. Well, say we have a series that looks something like this now, and we have to determine as to whether the series converges or diverges using the ratio test. So using the ratio test, we have to find the limit as n goes to infinity for the absolute value of an plus 1 over an. And here, if we do an plus 1, we're just adding 1 simply to all of these n's. So we're going to do that. So I added 1 right here to this n squared. And pi to the exponent of n is just going to be changed to n plus 1 right here. And then e to the exponent of n minus 1. This n is going to be substituted with n plus 1. And then we have to subtract 1 because it said subtract 1 there. And then here we have to add 1. Subtract 1 versus subtract 1 here. And we have to divide by an, right? It's a division line. So we're going to divide that. So basically, this an is our expression, so we're just going to copy that. And then to our next step. So we can recognize this as a division symbol. We could change to multiplication if we just flip the second fraction. And also in the meantime, we are going to simplify these exponents. So right here, we can see that pi to the exponent of n plus 1 is the same as pi to the exponent of n times pi to the exponent of 1. Because if we were to get from here to here, we would have to add the exponents. So that's how we get that. And here, the 1 and the negative 1 cancels out, so this is just going to be e to the exponent of n. And likewise, the 1 and the negative 1 here cancel out, so it's just going to be negative 7 to the exponent of n. We'll change this to multiplication. If we just flip this fraction, so we are going to flip. So write this at the top, write this at the bottom. And then once we do that, we can see that we can simplify pi to the exponent of n, cross these two out, and we will be able to simplify even more once we look at the next step and split up these exponents using exponent laws. Pi to the exponent of 1 is just pi, it's e to the exponent of n, and multiplied by negative 7 to the exponent of n times negative 7 to the exponent of negative 1, because here we can add these exponents together, n plus negative 1 together to get n minus 1 according to exponent laws. So we can split it up like this. Here we have 2n squared, copy that. And same concept here for e to the exponent of n minus 1. We can rewrite it as e to the exponent of n times e to the exponent of negative 1. That's because we can add these two exponents and we will get e to the exponent of n minus 1. And we're just basically undoing that adding by splitting it up like this. And so this will allow us to cross these two off, right? And we can also cancel this as well because they're the same. Negative 7 to the exponent of negative 1 is the same as negative 1 to the exponent of negative 1 times 7 to the exponent of negative 1. And that is because this negative 7 is the same as negative 1 times 7. And so, if we write this on the side, this is the same as negative 1 times 7, right? And if they were both being raised to the exponent of negative 1, it will look something like this. And since we have the exponent here and we have multiplication according to exponent laws, we can distribute this into each one. So it's going to be negative 1 to the exponent of negative 1 times 7 to the exponent of negative 1 like this. So that's how we get here, right? So this will just be negative 1 to the exponent of negative 1 times 7 to the exponent of negative 1, which is the same as this. So we got from here to here. And then we can see that this is just 2n squared, just copy this. And then e to the exponent of negative 1 is the same as 1 over e to the exponent of 1. And then now, carrying on, we can see that we have 2n plus 1 squared times pi times -1 to the exponent of -1, which is the same as 1 over -1 to the exponent of 1. And this is the same as 1 over 7 to the exponent of 1. This will be all over 2n squared over e. E to the exponent of 1 is just going to be e. From here, we have to evaluate the limit, and we know that if we plug in infinity into these ends, we plug it into the top, it's just going to go to infinity to the top, right? And if we plug it into the bottom, it's just going to go to infinity. Well, before we even do that, let's look at this -1 here, and we can recognize that this whole thing's just going to be -1, and there's an absolute value symbol. So if there's an absolute value, we just have to get rid of the -1 to make it positive. So all we have to do is get rid of this, and we have to get rid of the absolute value symbol to make the whole thing positive. So we don't need the -1 any longer now. This is all over 7. There's a 7 right here. And then we see here, this is 2n squared over e. And then following this, we see, right, -1, we got rid of it because it's the absolute value of that, so it would be positive. And then we can use L'Hopital's rule. In order to evaluate this limit, and that's because as n goes to infinity, top's just going to keep getting bigger and growing because n plus 1 squared is just going to get bigger, and as well for n squared it's going to get bigger, right? It's the top and the bottom is going to go to infinity, so we have to use L'Hopital's rule, so we're going to differentiate the top and the bottom. Also, before we do that, we see a 2 here and a 2 at the bottom. We can cancel those 2 as well. So differentiating the top and the bottom, let's differentiate the top. So using a chain rule, we bring down this 2. Right, this 2's gone, but this 2 is being brought down. It's going to be m plus 1 right here. Then we subtract 1 from 2, so it's going to be to the exponent of 1 here. And pi, which is being multiplied to it, so we're just going to leave it like that. Now, similar concept to the bottom. So to the bottom, we have n squared. So we are going to bring it down. It's going to be 2 over e, and this is going to be to the exponent of 1. And now we get here. However, we recognize that we need to differentiate this again because the top goes to infinity and the bottom also goes to infinity as n goes to infinity. So this would tell us that we need to use L'Hopital's rule again. So differentiating the top, we bring down this 1, and this is going to be n plus 1 to the exponent of 0. Okay, and obviously the derivative of n is just going to be 1. Just like we did before, derivative of n is just going to be 1, right? So we would basically have this, and then we have 2 over e. Because this n to the exponent of 1, 1's going to be multiplied, and it's just going to be n to the exponent of 0. So we get, in the end, oh, by the way, we can cancel these 2. So we are going to get, this is going to be 1 over 7. This is going to be 1 as well, times pi here, all over 1 over e. And then from here, we can divide. So pi over 7 divided by 1 over e. We're going to rewrite it like this. It's pi times 7, and pi times 1 here over 7, right? And then we can flip this second fraction again because we have a division symbol right here. We change to multiplication. So it's just going to be pi over 7 times e over 1. And there's no n to evaluate, so we could get rid of this limit. So it's just going to be pi over 7 times e over 1, which is going to give us pi times e over 7. And when you plug this into our calculator, this is going to give approximately 1.22. And we know 1.22 is our limit. Our limit is 1.22, and 1.22 is greater than 1. And according to the ratio test, right, we were trying to see where the limit for this whole thing is going to be greater than 1, less than 1, or equal to 1, right? So here in this case, it's greater than 1. Our limit is greater than 1. And if our limit is greater than 1, then by definition, this concludes that this given series is going to be divergent. So therefore, the series diverges by the ratio test. Okay, so this is the end of the video. If this video helped, feel free to give it a big thumbs up. Also, let me know in the comment section down below what you think about the ratio test and what you think about this video. And as always, if you haven't subscribed yet, if you are new to my channel, feel free to click the subscribe button if you enjoy my content. Thank you so much, guys, for joining me in this video. I hope you have a nice day. Bye!